灯在后面才给我中文。Okay, so now we're introducing three types of exposure systems. The first one is the contact printing system. The second one is a proximity printing. And the third one is a projection printing. So from the names of these three systems, we can get roughly the idea of how we name these kind of systems. The first one, contact printing, which means your mask and your silicon wafer, they are in contact. So the gap between these two is very, very small. Although there's certainly still a small, very small gap between these, but basically we try to make them in contact. So in this case, you can imagine that the features on your mask will be directly transferred to your photoresist, right? Because there's a minimum diffraction effect because the distance between them is very, very close. Okay, and then this gives you a very high resolutions. Okay, and without any it has a minimum diffraction effect. Okay, but in this case, you will not tolerate any defect in these systems, because once you have the defects in here, right, and you will affect the pattern, the final pattern. So we don't. We have to pay more attention about how to control your defect densities. Okay, and this kind of system requires less optics, so the cost is relatively reasonable. So in the university level, I think most of the contact we use this contact aligner in our curriculum for students to practice their device fabrication. And the second one we call it proximity printing, which means there's a gap between your mask and your silicon wafer. The gap is from 5 to 25 micron distance. And this will create from the light after they pass through this mask and reach to your silicon wafers. There exists a diffraction pattern, and this we call it Fresnel diffraction. So they will have this kind of effect, and so your feature size will be less accurate or less. The resolution will be lower compared to the one in the contact printing system. Okay, and these two systems, we call it like one-to-one exposure system, because basically the pattern you want on your wafers will be the same size on your mask. Okay, so there's like one-to-one ratios between them. And the third one, we call it a projection, which means you project the patterns using some optics and onto your silicon wafers. This one can give you high resolution as the one you get from the contact printing systems. And also because we like we mentioned before, we use a pellicle to protect our mask. So relatively they can tolerate some defects. So this kind of projection systems. And also in addition, the feature size on your mask can be larger compared to the actual size on your wafer. So through those optics, they can reduce the size. Okay, so this kind of projection system is dominant to date. But of course, this we have to consider the diffraction issues on these systems. So that's why if we consider those far field diffractions, we have to rearrange or correct the patterns on your mask. Okay, so the third one, this is very typical that we use in the foundries, and it's like a repeat and step or step and scan combined with these mechanical motors. So they can give you the high throughput and higher accuracy. Okay, so in this wafer exposure systems, we'll introduce some optics and some fundamental physics will be introduced here. Okay, so here is this light source that we used, and consider this is the mask, and we have some patterns, or we can consider an apertures on it. And the light going through this aperture and reach to your image plane. Okay. Typically, from the fundamental optics, we can use ray tracing. Okay, that's more easy to us to imagine that we can think the light travels in a straight line. Right, that's a ray tracing teaches. But as long as this dimension is large compared to your wavelength, ray tracing we can still use that. But once this aperture or these features become smaller and smaller, we cannot just use ray tracing. We have to introduce some like wave propagation in order to explain the result. So in that case, we have some diffraction effects begin to kick in here. So we will consider that a point light source, when the light propagates in the space, we can consider that the point source, and those point source, if you travel in the space without any obstacles, and okay, so all this wavefront will construct or deconstruct, and finally they still form a plane wave. But once you have aperture like here, then like this point source are blocked, and of course here, only the point source, the light can penetrate through these apertures. And since we consider it as a point source, so it will begin to propagate like this. And this wave will form the diffraction patterns. Basically, they interfere each other and form the diffraction patterns on your image plane. Okay. So if you have like smaller apertures, if this pinhole is smaller, then you will get a larger diffracted angles. Right? So that's the light can spread out in the wider angles. And then when you reach this image plane, then you'll see some. I think in the high school we already learned this in some experiment, right? So we introduce these diffractions. So a very simple example is this is a small circular aperture. Okay, we call it the airy disk. Okay. So we will form this kind of diffraction patterns, but in the center, the intensity is highest, and then they have some dark lines, and the first dark lines correlates to this distance. Okay, there's a certain math that we have to go through to give you this this radius If this is the center, then this is the radius of your disk. It's 1.22 times your wavelength and your focal length, and divided by the diameters of your lens. Okay, I think that's the basic we learned from the physics in your freshman year. I believe you learned this, or in high school you have learned this. Okay, so we will see this kind of we will use this kind of pattern to explain the resolutions later. Okay, so this kind of diffraction usually there's two limiting cases. The first one is the Fresnel diffraction, and the second one is the Fraunhofer diffractions. The Fresnel diffraction basically is a near field diffractions, and we will observe this in our proximity and contact systems. The first two, right? Because the distance between your mask and your silicon wafers is very close, so we can use these near field optics to explain this the pattern that we observed on our wafers. And so basically the light will travel through directly through the apertures and to your image plane. Okay, and for the Fraunhofer diffraction, we care about the far field diffractions, and usually we observe this in the projection system, the third exposure systems we just mentioned. Okay, so in that case, the light will pass through a lens, right, between the aperture and to your image planes. So the light will travel in a longer distance, and also there's some optics, some lens in between, right? So in that case, we have to use this Fraunhofer diffraction to explain the final features of your silicon wafers. Okay. Okay, so here is consider we have a point source. Although in reality there's no point source, there's no such a thing called point source. But we use this point source to describe this ideal case. Then after the collimating lens, this point source will become a parallel light. Right? So this parallel light will hit this mask or these apertures, and we have used this point source and the interference in the previous figures here to describe what will happen. So the light actually will, there is a certain diffraction angles. Okay, so this is a diffractive light, like this. Then we will use another lens, we call it like focusing lens. Okay, this is the basic the optics we can use in the projection system. Okay, so we have, although in reality there's more lens, more optics in these more complicated systems. But here we can use this to explain the idea. So we have a focusing lens to focus those photons and to on your image plane. So your silicon wafers will be placed in this image plane. Okay, and there's a certain size of your focusing lens. We call it D, which is the diameter of this lens. And this focusing lens is focal length is F. Okay. So in this systems, you can imagine that because of this diameter D is a finite number, right? You unless you have a like very huge, very large optics, but in reality it's impossible because you have certain constraint of your systems. So you will choose a certain diameter lens that for you to collect to focus the light back to your wafers. So these finite apertures, these finite diameters will create a problem, because from this figure you can see this part of this diffracted light is lost. Okay, and these diffracted lights, they contain certain information, especially for the high, we call it spatial frequency. Okay, high spatial frequency components. Okay, this high spatial frequency usually related to the smallest features. Okay, that will generate these high frequency components. So, from the explanation, you can imagine that since those high frequency components are lost, the information you actually collected and focused to your image plane will be those low spatial frequency components, and those smaller frequency spatial frequency component actually correlate to the large pattern, large size on your mask or on your aperture here. Okay, so your resolution will lost in this case. So I can use this to explain that. Consider we have a square pattern. Okay, so after your light going through these apertures, and that creates, there's diffracted light, and like this corner, like in the actual space, you have a very sharp change at the corner. Right, so those in a space is kind of like a step function, right? So you can imagine that you have to use more or higher spatial frequency in order to construct this kind of step functions or this kind of sharp corners. So that's the higher frequency regions that we will see from different apertures. So what I mean is this diffracted light with larger diffracting angles usually comes from this area. Like this, like small size or small apertures will give you a larger diffracted light. Okay, so I don't know if you get this idea. Okay, so I can use Chinese to explain again because I think this is quite important. Okay， 就是如果说我们有一个假如是一个方形的，好，我们先从一个圆形讲。如果是一个圆形的洞的话，我们知道这个洞越小呢，它这个diffracted 的 light 它应该会散的会越开。所以如果比如说我今天在这个上面，我有很多的不同的形状，那通常在空间上你有这种比较大变化的这个，它其实对应到就是比较高频的这个变化的量。那这高频的这种空间频率的变化呢，它通常就是对应到就是我们刚刚前面讲这个洞是比较小的，所以它会有一个比较大的散开的这个角度。所以今天这个绕射的光呢，因为我们的这个 lens 没办法做到很大，所以一定会有在边边的光是漏掉的。那边边光偏偏它就是对应到这些空间上变化比较大的，或是尺度比较小的这些绕射的光，所以那些光你就没有办法被收集起来，然后打到你的 image plane。所以简单来讲，就是 image plane 上面你看到的那个 aerial image， 它就不会是像这样，它可能就这边就变成 rounded 的，就变成4个角就变成是圆圆的，因为那部分的光你就已经没有办法被收集到了。OK， 所以这个其实这种课的一些东西，其实在类似像富士光学这种课，其实它都会跟大家介绍，或是像我不知道光电电磁学可能会教一些这种。I think so. That's the limitation of this projection systems. So in the TSMC, they have this OPC department. They can use some they can calculate this, use some commercial software. So back to this, we can redesign the patterns in order to compensate this higher spectral frequency loss. So maybe in the mask we can design like this. Okay, so we will draw these features on purpose. So it won't look like the original pattern, but like we have this small square on the corner, so it will look like this. Okay. Okay, so you add this correction component on your mask, and after the diffraction, that will give you the square aerial image on your silicon wafers. Okay. Okay, so okay. In the projection systems, we have this Fraunhofer diffraction dominance. So in that case, we will consider several things that will affect your final result. The first one is your resolutions and depth of focus and field of view, and this MTF, modulation transfer function, and alignment accuracy and throughput. Okay, so we need to consider these six parts. Okay, so the first one is the resolutions. So we can explain from these figures here. Okay, so consider we have 2 point source, A and B. Alright, so after the light goes through these apertures and being focused by the focusing lens, they will form the image plane A prime and B prime on this image plane. So this A will become the A prime here, and B will become the B prime here. Right? So if there's a diffraction effect on this during this process, then how can we resolve these two A prime and B prime points on your image plane? Okay, that's our questions. Okay, so here is the aerial image that we get from through this aerial disk. So if it is 1 point, you look like this, and if there are two points, A prime and B prime, for example, if this is A prime, this is B prime. In this case, we call it still resolvable, which means we still can identify there are 2 points on your image plane. Okay, so but if you get this 2 points closer and closer, in this case, in this C case, we say it's barely resolvable, which means if you get closer, we cannot identify it. We cannot distinguish these 2 points. You merge like 1 point, so it's very difficult for us to separate these two. So that's the criterion. We call it a Rayleigh criterion. Okay, so Rayleigh, this guy suggests that there's a reasonable criterion for resolution is that the central max of each point source lies at the first minima of the aerial pattern. Okay. So I think it describes this criterion very clearly, right? You have your central maxima, right? If you just lies at the first minima, this is the first minima, right, here and here. If you just touched here, okay, the peak where lies in the in the first minima, well, we can barely say, okay, there's probably two points that we can identify. So that's the criterion, or it creates a certain condition for us to make sure that if you have this diffraction effect, we have to make sure this it can pass this criterion. Okay, so that's the definition of the resolution we have in this projection system. Okay, so we will introduce a term called numerical apertures. Okay, so numerical apertures can be explained by these figures. If we have a lens D here and its focal length is f, and the angles between this line and this center line, we call it theta or alpha. Okay, there's a certain angle. So numerical aperture is a dimensionless number. Okay, that can be used to characterize the range of angles, which means the theta here, over which the system can accept or emit light. Okay, so if we want the numerical aperture as large as possible, so we can collect or emit light using this lens, these optical systems. So it is defined as this n sine theta. Okay, theta can be defined as the arctangent d over 2f. Here is d over 2, and d over 2f is this tangent. Okay, so back to the aerial disc problem. This is the radius that from these diffraction patterns that we learned from our high school. Okay, so now we can plug in this number. Okay, so this d here is the distance. Is the diameter of your optics, and you will be equals to is 2f sine alpha. Okay, so this alpha is the theta here. Okay, so we can f, and this is become like 0.61. Okay, lambda over n sine alpha, and this n sine alpha is the numerical aperture. Okay, by the definition that we explained earlier. Okay, so this is a resolution that we define in our projection system. Okay, so this the denominator is the numerical aperture, and this numerator is your lambda. Okay, so we can write this 6.61 as a certain parameter that we call it K1. It's actually an experimental parameter, which means it depends on your system, your lithography tool, and also your your photoresist properties. Okay, so this number is from 0.6 to 0.8 in between. So this resolution, in order to improve it, we have to decrease this K1. Right? We want this R as small as possible. So we have to reduce this K1 or reduce the lambda. Right? If it's smaller, your R can be smaller. Or you increase this NA, which means you need a bigger lens. If you have a large NA, means you can collect all the light, so it can give you higher resolution. Okay, so there are three parts that you can choose to improve your resolutions. Okay, so that's why we have to reduce the wavelength to EUV system. Okay, from like 193 is argon fluoride excimer lasers. Okay, so at that time, we say the textbook says under development, but actually we know it's well developed right now. Okay, and also, you see, back at that time, people still already talk about these extremely UV systems, right? It takes like 20 years to finally we have a commercial tool on this. So that you can imagine there's a lot of cost and investment in this, in the development of this tool. Okay. Okay, so that's the resolution part. And also we care about the depth of focus. Okay, so usually if we want the better resolution, we can increase this numerical aperture. But with higher numerical aperture, that will decrease the depth of focus. Okay, so depth of focus is defined as the distance in front of and beyond the subject that appears to be in focus. Okay, so there's a certain distance that you can focus your light on it. So you have to make sure your image plane is placed in this depth of focus. Okay, there's a range of it, so you have to place, or for the topology of your silicon wafers should be, in this in the range of your depth of focus, this DOF. Otherwise, your light cannot be focused very well on your image plane. Okay, so we can use this figure to explain what is depth of focus. So again, we use this focusing lens to focus the light, and this is the focal length of this optics. And so supposedly we have to place our image plane at this distance of focal F, so we can get a very well focused light on your image plane. Okay, but here you still have light because there's a certain distance of your apertures. Your light can be coming not just from the center, you're coming from the edge of your lens. So there's an angle theta here. Right. So if there's an offset of your image plane, let's say to this dash line here, we call it delta. So we want to find this delta because that's the allowable depth of focus that we can place our image plane. So here the dash line is the limit of focus, which means outside this delta distance, we can say, okay, it's out of focus. We cannot get very clear pictures, clear image on our image plane. Okay. So this is the, we call it, this is an on-axis defocus distance, delta. Okay, so if we have, this is the theta here, so delta times the cosine theta is the distance here. Okay, then we call this off-axis defocused. Okay, so in order to get a clear image, the light coming from this on-axis or from these centers, and there's a optical path distance difference of the photons or the light from this point. These two will try to, if they reach the image plane at the same time or within the certain optical path difference, then they can reconstruct a clear image. But if these two photons they reach to this plane at with different optical paths distance, then when they try to reconstruct the image, then the image will become like blurred because the phase, the phase delay is quite large. So you won't see a clear pictures. Let's say we'll call this out of focus, right? So, or we call that defocus or out of focus. So there's also a criteria suggested by Rayleigh. Say, okay, in order to make sure these two photons or two light from different angles reach on a certain plane, the difference between, the phase difference between these two has to be less than a quarter lambda. So once you put this light together, okay, they still can give you like a clear image. Otherwise, if it out of larger than a quarter lambda, then you will form the like very serious interference. Then maybe the intensity, the image will change a lot. So it's difficult for us to identify if it's the same as the original one. Right? So this distance and this distance, the difference is delta minus delta cosine theta. Okay? So delta cosine theta is here. Okay, and which means we try to calculate the distance between this on-axis path and this off-axis path. So the distance between them has to be less than a quarter lambda. Okay, so we can do some simple math calculation here. If this theta is small, which means if you compare the D and the F, if the theta is small, we can change the cosine theta into 1 minus theta squared over 2. Okay, so this will reduce to delta times theta squared over 2. And the theta here is the close to your tangent theta, which is close to your sine theta. That's the numerical aperture, and then we can use d over 2 divided by f to represent this numerical aperture. So we can plug this into this theta square here, then we get this DOF, depth of focus delta, is equals to lambda over 2 times NA squared. So this 1 over 2, we can use another parameter, K2, to generally express here, and that will be the experimental parameters. Also depends on your lithography tool and the optics you used here. Okay, so from this formula or this equation 5, you compare with this equation 2, right? So let me ask you a question. So you want this DOF large or small? Right? If you think you want DOF, for resolution it's easy for us to understand, right? You want R small, right? For DOF, you want large or small? Large, raise your hand. You want small? Anyone want small? Okay. So actually we want this, as large as possible, right? Which means we have this allowable defocus distance. It's not just because your image or your wafer you can change its position. Not just that, because that wafer can be controlled on your tool. The position can be controlled very well. Because sometimes if you already done the process, right? There's features on your wafers. There's a topology on your wafers. Sometimes you have etching depth, you have some mesa or change. Yeah, so if you do the lithography, you try to focus the light. Right? if there's there's a distance between your features from the bottom to the top. So if we happen to try to make a pattern that on those two levels, so in that case, you want your light can be focused on the bottom and also on the top. Right. So you want this DOF larger, so they can allow you to focus at the same time to get a clear image. Right. So, but if this DOF is very small, then if you focus on the bottom, the lower level, your upper level will defocus. You focus on the top, your bottom will become defocused. Okay, so in this case, we want this DOF try to be large as possible. But if you compare 4 and 5, they kind of contradict each other. Right? If you want this one to be large, like for example, if you want NA large, so you can get a higher resolution. Right. But in that case, your DOF will become very small. So that will create the problems. Okay. So you can use some other technique, or you have to modify your tools so that you can change this K1 or K2 parameters. Okay, here's just an example. If you use this lambda equals 248 millimeters with NA equals to 0.6. If you have a resolution like 0.3, if K1 is 0.75, and depth of focus like 0.35. Okay, to just you can get a sense of this. Okay, and the third one is the modulation transfer function. Okay, and this modulation transfer function is the measure of the contrast in the aerial image. So do you remember what's the aerial image? Okay, that's the 2D image on top of your photoresist. Okay, so ideally it should look like the same as you design on your mask. Right? But in practical, there's a diffraction effect. Okay, and so it measures the contrast. Okay, then let me use this figure to explain this. Okay, so this is the light intensity after the light just passing through the mask. So you can see that if your mask is designed like this, some transparent area and some opaque area, then if you check the light intensity just after this mask, passing through this mask, you will become like these figures. You have 0, which means low light. You have 1, which means the light will be the highest. Okay, in this transparent area, and there's nothing in between. So you can imagine that just pass through this mask, your intensity will look like this. But after the light travels into the space and also pass through this focusing lens, and when the light reaches to your surface of your photoresist, the light intensity, the distribution over the position actually will look like this. You have maxima and minima. The maxima will not equal to 1. And the minima will not be 0. There's a certain light intensity in between. Okay? And this pattern which is it's not desirable. That we don't want this to happen, because there's no light, which means we don't want there's a certain area that should not be exposed. But right now you have certain intensity at the position that we don't want there to be any light in that position. But now we have some intensity, which means it has some chance to expose at that area, which means the pattern will not be the same as the one that you design on your mask. Okay, so we will define this MTF as this contrast. Basically, just the contrast of this light intensity on the wafer. So we define this in equation 6 as I max minus I minima divided by I max plus I minima. Okay, and we want this as large as possible, and it should be larger than 0.5. Otherwise, maybe some exposure issue will happen. Okay. So why we have this kind of intensity distribution in your space? That's because you have this diffraction effect, right? And also this diffraction effect comes from the feature size of your design on your mask. Okay. And another thing is the spatial coherence of your light source, which means the light source will also play an important role. And what is spatial coherence? Okay, this figure used to explain the spatial coherence of your light source. Okay, so ideally we have the point source as our light source, as we use that to explain the fundamental idea earlier. And this spatial light, so after it passes through the condenser lens, then we create a parallel light. And those parallel lights will have no problem, right, when you pass through this mask. Okay, and those parallel lights, we say that they have very good coherence in spatial. Okay, so, but ideally the practical light source cannot be the point source, right? Because if it's the point source, basically the light intensity will be very, very small. You can imagine that. So there's no such thing we call point source. Point source means no light, because there's only one point, right? So you gotta have like a certain size of your light source in order to get your enough power or intensity. So in this case, your light source will have a certain diameter. We call it S here. Okay. So the light comes from this light source with different areas will actually be focused after they pass through this condenser lens, will be focused with different angles. And also this light is not a light source, so you won't be able to generate a perfect parallel light. So right now your light is not a parallel light. It has a certain angles to be incident on your mask here. Okay, so in this case there's a spatial coherence of this light source, because it's not parallel. Some it has like different angles from different, because it comes from different part of your light source. Okay, so you will not be plane waves anymore when they strike on your mask. So okay, we define this spatial coherence as the light source diameter S divided by D. this is a condenser lens diameter here. Okay. Okay, so come back to here. Because your light source is not a point source, so that will give you the non-parallel light when it strike to this mask. It will become like this. Okay, so in that case, that will also because the incident angle, the reason of that, you will have like minimal light in between these two patterns. Okay, so that will give you a modulation transfer function of your light, and that will affect the aerial image on your surface of your photoresist. Okay, but this is not a bad thing. You know, this spatial coherence is not a bad thing. As we can see from these simulation figures, okay, if you increase your light source diameter, then you become less coherent, and this MTF somehow will degrade for large features. Okay, so you can see from these figures, ideally is 1, which means your I minima is 0. Okay, so Ix divided by Imax equals to 1. So 1 is the ideal case, right? But once you have your feature size, become smaller and smaller, you can see this MTF will begin to decrease due to your diffraction effect. Then once you reach your silicon plane, then there's become a less contrast in your aerial image. Okay. So if we increase the S, okay, from this line to this line, we can increase the S, which means the less coherent light source you have right now. Okay, so you will see something interesting happen here. For the larger feature size, the MTF degrades as you increase your S, right? But for the smaller features, the MTF actually improves when you increase your S, your diameter of your light source. Right, so that's because if you have if it's not a parallel light, which means your light has a certain angle, and this angle will help you to focus those higher frequency, spatial frequency component into your optics, into your lens. Right. Let me go back to this figure to explain again. Okay, if you have a parallel light, then you have a diffraction pattern like this. So this higher spatial frequency component are lost in this system, right? And we just explained it. But right now, if you have it's not a point source, which means you have light coming through at different angles. So in that case, you kind of force those higher frequency light to, for example, here, this part of light will become like this. So part of this higher frequency now can be collected or can be focused into this finite diameter of your focusing lens. Okay, so that's a good thing for the smaller features. So you can see from here, actually there's a improvement for your small features patterns that you can increase the MTF. Okay. Okay. Now we change to the Fresnel diffraction. That's for our contact and proximity systems. Okay. So right now your mask and your silicon wafer. They are very close to each other. There's a gap, we call it G, between your mask and your resist. Okay, and okay. So right now since the distance is very close, so you won't create even there's an interference effect. It's not that serious because the light cannot pass through a longer distance now. And you already reach to your surface. So that creates an aerial image will be very similar as the pattern on your mask. Okay, but since there's a gap, there's some near field optics we need to consider. Okay. We still can use this point source to explain what's happening here. Okay, so there's still interference happens in your after the light passing through this distance G. Okay, and this interference will create this ringing because the intensity difference. There's constructive or destructive interference will happen. So those intensity here, you can see there's a ringing or there's a ripple here. And also there's a limited diffraction effect. So you can see there's light bending and reach a little bit out of your desired pattern, which is the dashed line defined here. Okay, but basically the pattern will look very similar to the mask, to the pattern on your mask. So that's the advantage of your contact and proximity systems. So in this case, we consider the Fresnel diffraction instead of the Fraunhofer diffraction. So if this G distance between is larger than your lambda but less than your this W squared over lambda. W is your aperture here. Then we can apply this near field optics. Okay, so we can quickly get you an idea that this W is equals to your square root of lambda times G. So if G is 10 micron and you use a line source, okay, so you have a W minima, it's around like 2 micron. Okay, it's not useful for our modern ICs, but it's good enough for you to make some device in the university level. Okay. So there's a figure below here is to try to summarize the three types of exposure systems. And there's a separation distance in between, which depends on what type of system we are talking about. Okay, so for the contact liner called contact system, that will create very similar pattern as the one you have on your mask. And for the projections, okay, the resolution it depends on your system, but it still give you a very good resolutions. But not as good as your contact, but it's good enough. We can use some OPC technique to improve that. Okay, the worst case is the proximity case, right? And so you can see there's a not ringing, and also the diffraction effect will cause your pattern critical dimension to increase. Okay. Any questions? Okay, now we move to the photoresist. Okay, so this kind of material is designed to respond to your incident photons. Okay, those photons we just explained earlier. There's a laser source, different wavelengths, or in different systems. Then when they respond or react to those photons, they will begin to change their properties when they're exposed to light. And this response has to be long-lived, which means once you change, then it changed. I don't want it to change anymore, so it can remain a very stable state, right? Before you do the development. Okay, and most of the resist are hydrocarbon based. Okay, you have hydrogen and carbon, this kind of compound materials. Okay, and if you have photons, incident photons will provide energy to break the chemical bond in between these molecules. So that will trigger some chemical reactions to change the properties. Okay, and we have positive tone and negative tone resist. And we choose positive tone resist because it's more soluble in the development solution. And typically it will give you a better resolutions. Okay, so positive resist is often used in the device process. And negative resist do the opposite way. Right? If you have a photo reaction, but become insoluble in your developer solution. Okay, so these they are liquid chemicals. You can use spin coating or spray, this kind of technique to apply it on your silicon wafers. Okay, so here just the processing step. So how you how do you spin coat your photoresist on your wafer? So you start with the clean wafers, and those clean wafers we just mentioned in the last chapter, and also we want to in the beginning of this chapter we say we have to use some heaters to heat up to over 100 degrees Celsius in order to dry out some water vapors. And then we can spin on photoresist, and a diffusion promoter may be used, or it depends, it really depends on the substrate properties. And because at certain photoresist, you can change the viscosity by diluting it or adding some solvent. Okay, so we can change the viscosity. And also the spin coater, you can change the spin rate. Okay, so both these will help you to determine the final thickness you want. If you have spin rate higher, then you can get a thinner photoresist on top of your wafers. And also you can spin longer, maybe give you a higher uniformity. Okay. Okay, so the film, it really depends on what types of photoresist you use, and also the spin rate you use. So sometimes it's like 1 micron, 2 micron, even you like 4, 8, 9, depends on what kind of process. Like if you want use that to block some ion implanter, right? Use that implanter, then you probably need a thicker photoresist. Okay. And after you apply spin on this photoresist, we will move it to a heater, try to do the pre-bake to drive off some solvent. Because photoresist, in order to make it easy for us to spin coat on the wafers, we will add some solvent. Okay. And then we can do the alignment and exposure in the three types of exposure system we just introduced. And there's a possible post-back, which means sometimes we'll use that to enhance some chain reaction in your chemicals, in your photoresist. So a possible post-back, sometimes we'll use that. And then we can do a develop in the developer. Okay, that is to remove unwanted photoresist. Okay, it's also a chemical reactions. Is a developer usually is an alkaline solution. Okay, and possible resist trimming, which means sometimes you want to reduce the critical dimension or the minimal feature size. And because of limitation of your exposure tool, okay, that will give you like certain critical dimensions. But if you want the dimension even smaller, what can we do? Okay, we can use some resist trimming, maybe in the some RE chamber. You can etch away part of your photoresist. For example, if this is the photoresist, after you develop, there's another photoresist. If you use the maybe oxygen plasma trimming, you can make it like even smaller. So you can etch away this outer part. So you can trim the photoresist to make it even smaller. Okay, so that's doable, but you need to develop and control that trimming process. Okay, and after developed, we will go through some post-back to harden as an etcher mask. For example, in the same case here, if we want to etch, use plasma to etch maybe the silicon underneath, go to etch this part, or want to etch away this part. Then we have to make this photoresist harder. So this one way is you continue to bake it. You can make it, even harder. That can resist your ion or plasma bombardment. Okay, so then you can do the etching. For example, you can do the etching to remove the unwanted silicon region here. And then once you finish your etching, you can remove the photoresist. Okay, either chemically or in the oxygen plasma. Because we have a carbon and hydrogen. If you use oxygen, that's very easy to react with this kind of material and become volatile in your chamber. So you can remove your photoresist using oxygen plasma. Okay. So these are some parameters that we care about for the photoresist. The first one is the sensitivity. How good does it react with your photons? Right? It is very sensitive material, which means you can use less photon energy, less dose in order to expose the resist. Right? If it's not that sensitive, then maybe you have to use your dose time has to be increased. Okay, so that related to how much light is required to expose the resist. When you say expose, which means you can, then the chemical reaction fully happened, and make sure the area you want to expose that the material property will change totally. Okay. And typically for the G line and I line, that's the 100 millijoule per centimeter square. That's the minimum intensity required for the photons or for the light in order to react with your photoresist. Okay, but sometimes if it's too sensitive, or it becomes very unstable, and also it's temperature dependent. Okay, so this kind of photoresists are very sensitive to UV light. Okay, so that's why we have if you go to the clean room for the lithography, if you're doing the lithography, the light is usually in yellow, because in yellow you try to yellow is the complementary light of your blue and purple UV light, right? So basically, if you screen out all the UV light in that room, it looks like a yellow, right? So it's a 黄光哈，你就去看那个做制成的，在曝光的地方，它一定都是黄色的光线，因为它就让里面不会有这些紫外光啊，这种偏蓝偏紫的光存在，所以你把那个光滤掉，你就是另外它的互补色，那个黄色光就跑出来，所以你就看到那个为什么都黄黄的，或者都有个黄色的，其实就是怕你的 photoresist 在里面太 sensitive， 如果任何空间中有一些紫外光，它可能就被曝光了。它如果有被曝光之后，你的 sample 就没办法用了嘛，就是你这个光组就没办法用了，后面就没办法真的来做制成。Okay, so what I'm just saying is we have to create this kind of spatial region or room that without any UV light. Otherwise, these photoresist can be very sensitive to that. And also, we will use some glass in brown color that to hold this this container for the photoresist. This is the same purpose. You don't want that to be exposed before you really do the exposure. Okay, and some resolution is also very important. Okay, that all depends on the properties of your resist. Okay, so we want this diffraction limited resolution in the resist image. Okay, so the diffraction limited resolution means it's better be limited by your diffraction, not by your photoresist. Okay, your photoresist has to be way better, provide way better resolution than that. Okay, and the third thing that we need to consider is the resist capability, which means it has to withstand or sustain in the following etching process, or like an implantation process, right, after post-bake, right? Otherwise, your resist has no function. Okay. Okay, so now we'll introduce this G line, I line resist first. Okay. Okay, so in the resist, it generally consists of three components. The first one is the active resin. Okay, so that's the fundamental composition in your photoresist. And the second part is the photoactive compound, which function as the component that can react with your photon. So we need to have this photoactive compound attached on your basic resin, right? On your basic chemicals. And the third one is the solvent, which you use to adjust your viscosity. And that will evaporate in the spin or pre-bake. Okay, in the previous process, we'll do some pre-bake to drive out the solvent. So solvent is help you to adjust the viscosity, also to change the thickness and in final thickness. Okay, so you can add solvent or you can change the spin rate that can adjust the final thickness. So basically we have these three parts in your resist. Okay, and after spin and baking, pre-bake, we drive out the solvent. We have PAC, this photoactive compound, and the basic component about a 1-to-1 ratio. Okay, and this DNQ resist are commonly used today for G line and I line. This DNQ stands for this. I think that's from the chemistry, right? We don't really need to know this chemistry, but we need to know how it functions when you do the lithography. And this base resin is normal lac. Okay, I'll try to use the Chinese to use 树脂啊，这种 resin 都是这种树脂。Basically, it's a long chain polymer. Okay, it's a polymer that has hydrocarbon rings. This kind of hydrocarbon rings and two metal grooves and one OH groove attached. So that make you become that dissolvable in the developer. There's a certain rate, like 15 nanometer per second. Okay, so that's the normal lac chemicals that shown here. Okay. Now, once you have this, we have another. This is the photoactive part that will attach on this long chain polymer. Okay. This PAC is diacetyl chronomix. I don't know. Actually, I don't understand these chemicals, but we have this PAC part. So we use this R to represent this long chain polymer. And this for the active part, we have this oxygen and nitrogen molecular on the outside of this chain. Okay. So basically, this kind of DAC is insoluble in the typical developer. Okay, so once they attach on this polymer, that will reduce this dissolution rate down to 1 to 2 millimeter per second. Okay, but after we expose the light of this photoresist, this PAC will undergo a transformation, and this transformation is it's a famous transformation. We call it Wolf rearrangement. Okay, this Wolf rearrangement, we can see like here you have a photon come here and you will break the bonds. Now this nitrogen molecular will be gone. Then this electron will move to here. Okay, and that will create this carbon and oxygen bond, and also they will attach another OH. Okay, so here it becomes this COOH. Okay, this COOH is the this carboxylic acid, and it becomes soluble in the developer because the developer is a basic solution. Okay, this basic means base 就碱啊，alkaline， 也可以叫 base， 所以它 it becomes the developer is a basic solution, and this is the acid, so it becomes like a neutralization process when you do that in the developers, because this COH will react with your developer, and developer is typically this TMAH, okay, this tetramethyl ammonium hydroxide, or this KOH and AOH based. Okay, and once the exposed resist, now the developer rate or the dissolution rate will increase like 2 orders, from like 1 to 2 nanometer per second, and increase to like 100 to 200 nanometer per second. Okay, so that will create this kind of dissolution rate difference between the area that being exposed and the original material. So once you put that in your developers, those exposed area will dissolve very fast, and maybe after a certain amount of time, they'll be all gone, and you can take the wafer out of your developer. Okay. Now move to the DUV resist. Okay. This G line and I line resist we just explained, they have maximum quantum efficiency less than 1, usually typical 0.3. Okay, and for the DUV resist, we try to improve this quantum efficiency by introducing a chemical amplification process. Okay, this chemical amplification process we'll explain later. Basically, we have to use a catalyst in these chemicals. Okay, and this DUV resist, which means DUV means the wavelength is even shorter compared to your G line, I line. This DUV resist, they have a PAG instead of the PAC photoactive component. We have photoacid generator PAG molecule attached on your DUV resist. So this polymer chain is insoluble in the developer because these attached molecules, they are similar as the one we explained here. Once you have the PAG attached, it becomes almost insoluble in your developer. Now, if you have incoming photons that will react with this PAG molecule and create an acid molecule, and this acid molecule will act as like a catalyst and initiate a chemical reaction that makes the resist soluble in the developer. So it's a catalyst action, so you can increase the sensitivity, you can increase the efficiency. Okay, so we can use this figure to explain this. You have the PAG molecule here, and that's insoluble in your developer. So once you expose, the photon will react with this PAG, so that will generate this acid. And during the exposure, post-exposure bake, you provide heat and energy to this acid, and that will trigger a chain reaction. So this acid will become soluble, and that will trigger another one to make this one become an acid. And you will continue to do this, and those acids will now become soluble in your basic solution, in your developer. So that will underneath this kind of chain reaction during your post-exposure bake. So in that case, you can increase the efficiency in your DUV resist due to this kind of chemical amplification process. Okay, so for the negative DUV resist, the PAG can catalyze as a reaction which cross-links the polymer chain and make it insoluble in the developer. So in the negative DUV, that does the opposite way, right? previously this is explained in the positive resist, but for the negative, you create a cross-link of the polymer and make it even insoluble in the developer. Okay, so compared to the previous G-line and I-line DAQ resist, the required dose for your incident photon is 100 millijoule per centimeter squared. But right now for this DUV, with the help of chemical application, you can increase the sensitivity. So right now you don't need higher optical power in order to expose your resist. Now the dose can be reduced to 20 to 40 millijoule per centimeter squared. Okay. And that's the basic parameters to describe the resist parameter is the contrast and this critical modulation transfer function. We call it CMTF. So in the exposure system, we describe MTF, but right now for the resist, there's another figure of merit, we call it CMTF, critical modulation transfer functions. Okay, there's a similar idea, and we'll see that later. Okay, so the contrast, it can help us to distinguish the light and dark area on the mask. So from this figure, that means this slope. Okay, let's explain this figure first. Okay, so on the axis, axis, that's the exposure dose that we need, and here is the fractional resist remaining, which means this experiments can be done by you have a encoded resist on your wafer, and you continue to increase the exposure energy. Right. So in the beginning, and once you expose in your system, then you can put into the developer, and after a certain of time, you can bring it out and measure the remaining thickness. Right. So if your dose is not high enough, it's not even to begin to expose and to develop. So you can see that the remaining fraction is almost 1, which means there's nothing happen. But once you reach to this Q0, which means the threshold dose that you reach, and now you begin to have some reaction in your resist. So after this amount of dose, you begin to expose and react with your developer. So like these figures for the positive resist. Once you take it out from developer, you measure the remaining thickness. Okay, then this part of this the resist has already been dissolved in your developer. So you can see this line begin to decrease, which means more and more photoresists are exposed and developed in your developer. So you have the remaining fraction become smaller and smaller. Okay, so you continue to increase the dose until you reach the QF. So the QF means okay, now all the resists are gone in the developer. Okay, so now we can draw this line Q0 and QF. Okay, so QF means, and this you have to provide this kind of dose, exposure dose, so you can fully develop your resist or fully exposed in your resist. Okay, so the contrast will be this slope. Okay. Okay, so we can use this equation 11 to define the contrast or the slope. Okay, so QF divided by Q0, and you take log 10, and the inverse of this is, we call it gamma. Okay, for G line and I line, the gamma is around 2 to 3. Okay, and the QF is like 1 millijoule per centimeter squared. But for the DUV resist, they give you much higher contrast value, from 5 to 10, and the QF is 20 to 40 millijoule per centimeter squared. Okay, and this gamma depends on the development chemistry, your bake time. Right? If you bake longer, then it becomes harder. The dissolution rate will be smaller, and also the temperature before and after exposure, or the wavelength of the exposing light, or the underneath structure of the wafers, that will affect this slope, this gamma, this contrast. Okay, so the figure on the right hand side describes the negative resist. So this just work opposite, right, the other way. Okay, I think it's time for us today, and so we don't have a second break, but we can just stop right here, and we will continue this on Monday. Okay.